Good morning, afternoon, or evening, or whatever it happens to be where you are. This is going to be the first video on my redo of my APC Physics Electromagnetism playlist. What's going to be different about this is I already have the answers typed up, so it will minimize my chicken scratch handwriting that I'm using with the mouse, although there will be some of it. But without further ado, let's get started. Let's start with the idea of electric charge. Electric charge, we usually use the symbol Q as a fundamental property of matter, carried by particles like electrons and protons. Again, if you remember from your chemistry, if you took chemistry, you will know that electrons and protons are part of atoms. Electrons are negatively charged, protons are positively charged. And these charges experience a force when in an electromagnetic field. We will talk about what an electromagnetic field is now, but for now, let's just say charges experience a force within the presence of other charges. The MKS unit of electric charge is the Coulomb. Its symbol is C. Charges, again, can be either classified as positive or negative. Like charges have a force of repulsion. They repel each other, and unlike charges have a force of attraction. Coulomb's law. Coulomb's law is for electrostatic forces. The electrostatic force is what I'm calling Fe, K Q1 Q2 over R squared. R is the distance between them, and this vector R hat, it's a unit vector, and that just shows the direction this vector goes is along the distance between them. That sounds redundant, but it isn't, because later we're going to talk about magnetic forces that are perpendicular. Okay? K is the Coulomb constant. It's 8.99 times 10 to the 9 in MKS units. And if you remember from your mechanics, MKS means meter, kilogram, second. All the other units are built up from meter, kilograms, and seconds. And that includes coulombs. And it's also 1 over 4 pi epsilon naught. This is epsilon naught. Epsilon naught is what we call the permittivity of free space. Okay? What that says is how easily the electric field can transfer through something. Okay? That'll make sense. That'll make more sense when we talk about dielectrics later on. But here are its units in MKS. 8.854 times 10 to the negative 12. Now if you notice, this electrostatic force looks very similar to the force of Newton's law of universal gravitation. They are not the same, but they are inverse square laws. If you remember this from your mechanics classes. M1, M2 over R squared, where G is the gravitational constant, which is 6.67. Can't make a decimal point. Yeah, drawing with the mouse is not fun. Times 10 to the negative 11. In MKS units. Now, two 1 kilogram spheres each carry a charge of magnitude 1 Coulomb. How does the electric force compare to Fg, the strength of the gravitational attraction? How do the electric force and the gravitational force compare? Now, let's look at this. Here's the solution. Fe over Fg. K Q1 Q2 over r squared, G m1 m2 over r squared. 1 Coulomb over r squared, and the r squareds cancel out. Okay? And since these two are forces, there are no units. Again, the units cancel out. Newtons over newtons means no units. And it's just K over G, provided we keep the units consistent. And we get 1.35 times 10 to the 20. Now, that's when using MKS units with kilograms and coulombs. If we're actually using natural units, it's even bigger. Okay? The elementary charge and the Planck mass. We're going to talk about the elementary charge, but really not the Planck mass later. Okay? Moving on. Two charges. One of 5.46 microcoulombs and the other of negative 6.47 microcoulombs are separated by 10.2 centimeters. What is the force between them, and is it retractive or repulsive? Okay? And number 3, if the 5.46 microcoulomb charge has a mass of 284 grams and is released, what is its acceleration? Now, the first question 2, Sherman question, was actually the easiest. Is it attractive or repulsive? Since we have a positive and a negative charge, that force is attractive. Okay? Now here are the solutions. F, electrostatic force is K Q1 Q2 over r squared in the r hat direction. We don't care about that. It's going to be 8.99 times 10 to the 9. Okay? That's our Coulomb constant. Now, 5.46 microcoulombs. I have this 5.46 times 10 to the negative 6 coulombs. Okay? These units are in coulombs now, not microcoulombs. Because they're in coulombs, because we need to keep that and everything in MKS so it's consistent with this constant. Okay? Now, 10.2 centimeters is 0.012 meters. These units are meters. Again, you have to keep it all in MKS. And I get negative 30.5 newtons. The negative here indicates that it is an attractive force. They're pulling inward. Acceleration is force over mass. And it really doesn't matter here. 30.5 over 0.2.84. And what do you know? I don't have a answer for this, but you can put this in your calculator. This is just Newton's second law, and it's going to be, give me one moment, just put in your calculator or computer algebra system, and the answer is 107 meters per second squared. Moving on. Superposition. Okay? Superposition in electric forces means the net force on any charge is the vector sum of the forces surrounding the charges. If we want to find all the forces on the charge Qn, we add up all the charges, okay? And this is actually RKN, okay? From K, KN. Okay. From charge K to charge N, for all the other charges, 1 to N minus 1, okay? and we have to add these vectorially. See, here n is 3. We're trying to F the total forces on charge 3, F3, is F1 3 and F2 3, and these add vectorially. We have to resolve them into components and add them. And if you remember your vector addition from mathematics, that can be tricky because you have to resolve into components and add. 3 charges. One at the origin of the Cartesian plane of 2 microcoulombs, one at 3, 2 microcoulombs, okay, one at 3-4 centimeters of negative 1.87 microcoulombs, and one at -2, -3 of 4.23 microcoulombs. What's the magnitude and direction of the force at the charge of the origin? So you have a charge at the origin of a Cartesian plane, 2 microcoulombs, at 3 centimeters, 4 centimeters, negative 1.87 microcoulombs, and -2, -3 of 4.23 microcoulombs. What's the magnitude and direction of the force of the charge at the origin? How are we going to set that up? Here's how we do it. First, let's look at the picture. We have the charge at the origin. That's going to be your Q3. That's the force we're trying to find the charge on. Okay? And F1 is F13, F1 is F3. I'm finding the forces on charge 1. Yeah, I did a different number system here from, this is force 2, 3, this is force 1, 2, this is force 1, 3. Okay? F1, this is F1, 2. I'm calling, and this is F2, 3. F1, 3, sorry. I'm finding I'm calling charge 1, the one, the origin, the one we're finding the forces on, okay? Then we add these up, okay? K Q1 Q2 over R12 squared, K Q1 Q3 over R13 squared, okay? Let's look at the drawing here. Here's Q1, okay, at the origin. Notice Q1, again, terrible drawing, Q1 at the origin. That's where we're looking, the charge we're looking to find the force on. Notice this is a positive charge, this is a negative charge. Forces flow, we're going to talk about this more later when we talk about fields. Forces flow from positive charges. They flow into negative charges, okay? We're going to make this clear later. Sources, positive charges are sources, negative charges are sinks. That's something we're going to talk more about when we talk about field next time. But let's look at this. The radius between 1 and 2 is the cosine of the angle times the x hat direction, the sine of the angle times the y hat direction. It's the cosine of this angle. This is your theta 1, 2 right here. So we need the cosine of that angle and the sine of that angle. And again, use your theta 1, 3 here. Okay. And we know this is 2 over 3, okay? I'm sorry, this is theta 1, 3, sorry. Theta 1, 3, and this is theta 1, 2, okay. This is Q, this is charged. This is charge 3, and this is charge 2. We need to find out how 3 and 2 are going to be in charge 1, okay? And again, we have, this is a 3, 4, 5 right triangle. 3/5 x hat, 4/5 y hat, and 2 root 13 x hat, or 3/113 y hat. Okay? Adding this all up, okay? R here is 5, R12 is 5, and R13 is root 13. We know that by Pythagorean theorem, because this is 3 and 4 here, and this is 2 and 3 here. We know that by Pythagorean theorem. Now we have our F. Here. Now, we add these together. We have to add them component by component. Okay? And here we have it. The final force is 40.5, 62.3 in the y-hat direction. Magnitude is also Pythagorean. And the angle, the way it goes, is the arctangent of the y over x, and that's going to be 56 degrees from the horizontal. Okay, that sounds complicated. And again, that's a vector addition. You have to resolve it to components. First, figure out what the forces are, find them in component form, then add them component by component. Like, for example, remember how we add vectors? This vector, vector v1, v2 here. The resultant when you add them is here. Okay? You have to resolve both v1, v2 into components and then add them component by component to find the components of the resultant. Okay? Moving on. What will happen to the magnitude of the electric force between two particles if the distance between them is doubled and the charge is tripled? Okay? New F old, we have, instead of Q, we have 3Q. Instead of R, we have 2R. And then the answer is 9/4. Thank you. I hope that was of use to you. And if you like my style of teaching and would like to hire me to tutor you, my contact information is on the screen. So if you want to get in touch with me, my rates are reasonable. I look forward to hearing from you. And yes, we can go over these problems with many more steps and in much greater detail in a private session. And hopefully in future sessions I will have some animations. I'm trying to learn animation right now. So if this was unclear to you, it might be clearer when I talk about the rest of the class. Talk about the topics in the rest of the class. Thank you.